At the beginning of the last lecture, I mentioned that in our second week, we will be focusing on 4 concepts: the relationship between stress and force, the relationship between displacement and strain, equilibrium equations, and constitutive law. We will talk about the first 2 topics last class. So in today's class, we will look at the later 2 concepts, equilibrium equations and constitutive laws. Now let's talk about equilibrium equations. If we imagine a particle with a mass of m4, and this particle is subjected to 4 forces from other particles, F3, F4, F6, and F7. Then, based on the Newton's second law of equilibrium, all the forces acting on this particle is equal to m4 times its acceleration. Along each direction, we will have its component form. So in x direction, we have the x component of the acceleration times m4 is equal to the x component of f3 plus the x component of f4 plus the x component of f6 plus the x component of f7. In y direction, we will have the y component of acceleration times the m4 is equal to the y component of f3 plus the y component of f4 plus the y component of f6 plus the y component of f7. And along z direction, we will have the z component of acceleration times the m4 is equal to the z component of f3 plus the z component of f4 plus the z component of f6 plus the z component of f7. The extension of these equations to continuum allows the study of the deformation of objects by studying the motion of the relative particles on a continuum with respect to each other. When we are studying the mechanics of a continuum, we are usually interested in the deformation of that continuum after applying external forces onto the object. Euler basically stated that you can treat any part of the continuum as a particle and apply Newton's law of equation onto that particle. Now let's take a look at a differential equation of equilibrium in a continuum. We are going to extract a differential volume and look at it under the microscope. In order to develop differential equations of equilibrium, we need to assume that the stress in the continuum is smooth and that it is differentiable. Let's take a look at an example here. If we plot the relationship between sigma 1,1 along x1 axis, we can see that stress is a continuous function that is differentiable. When given a position such as x, then the stress at this particular point, sigma 1,1 x1, we can get this value. And if we have a tiny increment of a delta x1 at this particular point, x1 plus delta x1, we will get sigma x1 plus delta x1. Knowing the stress sigma is differentiable, then we can use the stress at point x1, sigma x1, to express the stress at sigma 1,1 at point x1 plus delta x1 using Taylor extension. So it's equal to this sigma 1,1 x1 plus delta x1 is equal to sigma 1,1 x1 plus partial sigma 1,1 over partial x1 times delta x1 plus other terms. Since we have a very small delta x1, so the other terms will have limited effect in this situation. So we can ignore them here. Now let's go back to the cube that we extracted. If the dimension of this cube is dx1, dx2, and dx3, and we define rho as the density and b as the body force factor per unit mass with the 3 components, b1, b2, and b3. Then we know that body force per unit volume acting on this cube is rho b1, rho b2, and rho b3. If we recall Cauchy stress that we learned in the previous lecture, we know that Cauchy stresses at one point can be expressed using 6 independent components. So we can put these stress tensors on the bottom 3 faces of the cube. Then, if the cube is in equilibrium and under external forces, the stress tensor on 3 front faces will be slightly different from the bottom 3 faces, and they have following forms using Taylor expansion. So for example, on the right face, we have one normal force, which is sigma 11 plus partial sigma 11 over partial x1 times dx1. And we have two shear forces. So one is sigma 12 plus partial sigma 12 over partial x1 times dx1. And the other one is sigma 13 plus partial sigma 13 over partial x1 times dx1. And similarly, on the front and top faces, we have a similar expansion. Then we can get the equation of equilibrium. For equations of equilibrium along x axis, we have 7 forces in total. So let me erase this first. So we have sigma 11 along the x1 axis, and we have a sigma 21, and we have a sigma 31. And for the stresses on the front faces, we have sigma 11 plus partial sigma 11 over partial x1 times dx1, and sigma 21 plus partial sigma 21 over partial x2 times dx2. And we have sigma 31 plus partial sigma 31 over partial x3 times dx3. And we also have a body force. So the summation of all these 3 forces is equal to MA1. So because we have stresses on these cubes, please don't forget to multiply it by the area of the cube. And we know that, so we can count now after simplification, we can cancel this one. And we can cancel sigma 21 and cancel sigma 31. So, and we know that the mass is equal to the density rho times the volume of this cube, which is dx1 times dx2 times dx3. And then we can plug in m and divide the volume on both sides. Then we will have this term left, because this is the volume. This term left. This is the volume. And this term left. this is volume, and this will become rho. This will become rho as well. Then after simplification and rearrangement, we get this form. So partial sigma 1, 1 over partial x1 plus partial sigma 2, 1 over partial x2 plus partial sigma 3, 1 over partial x3 plus rho b1 is equal to rho a1. Similarly, using equilibrium in y and z direction, we can get second equation and third equation. We can also write these three equations in a more condensed form. So if we let I is equal to 1, 2, 3, and then we can express every single equation as a summation from when j is equal to 1 to 3 of a partial sigma gi over partial xg plus rho bi is equal to rho ai. So if we introduce a divergence operator, we can also express the above equations in this form. So they are the same thing, but used a different notation. For equilibrium equations in static, acceleration is equal to 0. So the above equations can be simplified. And the right side of the above equations are all 0. If we take a look at these three equations of equilibrium, we can note that there are two difficulties associated with solving the equations. First, for a general state of stress, we have 6 independent unknowns, but we only have 3 equations here. Thus, it's a redundant system, and there are many solutions that satisfy these 3 equations. The second issue is that some boundary conditions contain expressions of displacement, while the equations themselves in this form do not have displacement as variables. In order to solve these 3 equations, we can choose either simplify the unknowns to 3, or by making assumptions, or introducing new equations. Now let's take a look at a few examples that with a strong simplified assumption. So for our first example, here we have a vertical beam that has a decreasing cross-sectional area with a top radius of 2 meters. This is 2. And a bottom radius of 1. So here it's 1. The beam is used to carry a concentrated load of P, which is 50 Newton. The beam density is 20 kilogram per cubic meters, and it is subjected to a gravity field of G at 10 meters per second squared. Assuming that the only non-zero stress component is sigma 22, where sigma 22 is a constant for every cross section perpendicular to E2. And the undeformed and deformed coordinates coincide. Let's find the distribution of a stress component sigma 22 along the length of the beam. I'd like to point out here that the assumptions in this question are quite restrictive, and you are not likely to see these kinds of boundary conditions in real-life situations. Now, let's take a look at how to find sigma 22 for these questions. So, as the cross-section area of this beam is changing, So first thing, we needed to find the expression of a cross-section area with respect to the position. So for example, if we have a position here, which is x2, and we need, in order to find the cross-section, we need to find the radius first. So r, and we need a line here in order to find the radius. So if we denote this part as delta, and we know this part is 2 minus 1 is equal to 1. And then we can find the relationship between delta over 1 over this distance is equal to this distance, which is L minus x2, and divided by the entire length. This is the delta, and the radius is equal to 1 plus delta. Then after rearrangement, we get r is equal to 2 minus x2 over L, and then we can get the cross-section area at any position is equal to pi times the r squared. Next, we need to find the equilibrium equations. So we take a horizontal slice of the beam, and we find the stress. If we know that this differential volume is in equilibrium, then the stress on the top surface is sigma 22, and the stress at the bottom surface is equal to sigma 22 plus partial sigma 22 over partial x2 times the length dx2. And since the cross-section area is varying, so if we assume the top surface is A, the bottom surface will be A plus the partial A over partial x2 times the dx2. And don't forget, we have a body force here. It's equal to rho times g times the cross-section area times the length dx2. Then, so using the equilibrium along x2 direction, we have this form. The stress sigma 22 times cross-section area A, which have the opposite direction along to x2, so it's lactive, plus the body force rho times g times A times dx2, and plus the normal force acting on the bottom surface, which is equal to the stress on the bottom surface times its cross-section area is equal to 0. Then after simplification and rearrangement, we get partial sigma 22 over partial x2 times A plus sigma 22 times partial A over partial x2 plus rho times g times A is equal to 0. We know that in order to solve this differential equation, after integration, we need to introduce one constant, C1. So in order to fully solve this, in order to find C1, we need one boundary condition for this differential equation. So if we take a look at the question again, we notice that at when x2 is equal to L, we have sigma here is equal to P over the cross-section area. So when x2 is equal to L, sigma 22 is equal to P over pi. Then using these two equations, 1 and 2, 1 and 2, we can fully solve sigma 2, 2. So if we take a look at these two equations, you can notice that even with the very simplified assumptions that sigma 2, 2 is the only non-zero component of the stress vector, non-zero component of a stress matrix, the differential equation is relatively complicated. So here I use the dsolve in Mathematica to solve this. And after solving the equation 1 and equation 2, I get sigma 2, 2 is equal to this. So I also posted a Mathematica code that I used here. So here we only have one key command. So in order to solve a differential equation, you need to use the dsolve in Mathematica. And here is the differential equation. And here is the boundary condition. And we solve stress sigma 2, 2 with respect to x. Yeah. If you are interested, you can give it a try after class. Now let's take a look at second example. The horizontal beam shown here has a density of rho is equal to 1 kilogram per cubic meters, and is under constant horizontal body force component B1 is equal to 10 Newton per kilogram, assuming that sigma 11 is the only non-zero stress component, and that sigma 11 is only a function of x1, and the undeformed and deformed coordinates coincide. Find the distribution of sigma 11 along the beam. So for this question, we need to do the same thing. We take a vertical slice from this beam, and we notice that we have stress sigma 11 on the left face, and the stress on the right surface will be sigma 11 plus partial sigma 11 over partial x1 times dx1. And we also have a body force which is equal to rho times b times cross-section area times the length of this differential unit is equal to dx1. And cross-section area is the same for both faces. Then use the equilibrium, we can get this differential equation. So partial sigma 11 over partial x1 plus rho b1 is equal to 0. Since sigma 11 is only the function of x1, so we can change it to this form. Then after integration, we will introduce one constant, which is c. So in order to solve c, we need to find one boundary condition. So we noticed that at the end of this beam, sigma 11 is equal to 20 Newton meter. So when we plug in this boundary condition, we get c is equal to 70 Newton per meter squared. Then we can find sigma 11 is equal to minus 10 times x1 plus 70 Newton per meter squared. This one is relatively simple, so you can solve it by hand. But here I also use the Mathematica code to find this the answer. So we have one. So I use the dsolve, And we have one differential equation and one boundary condition, and we solve sigma 1, 1 with respect to x. And after solving this, you will get the same answer as what I show here.